Hey everybody. So we are starting a new chapter and we're going to be talking about organic acids and bases. So we have been dealing with acids and bases and titrations and that sort of thing for quite a while. And we've sort of been introduced to the concept of weak bases through our titration with acetic acid. Acetic acid is different from the typical acids we've been dealing with in that it's weak. One of the weak acids we've dealt with is phosphoric acid, but phosphoric acid doesn't have any carbons in it, so it isn't organic. So we're going to be talking about the properties of organic acids and bases, some of the derivatives that they form, and then some of the reactions they undergo as well. And we're also going to do that in lab this week. So we're going to learn to identify some of these carboxylic acid derivatives. We're going to be learning how to name them. And of course, the naming of these things is always kind of tricky. So I'll try and go through that part slowly and reasonably as I can. And then we're going to be looking at some of these reactions of the products of carboxylic acids, because a lot of them are really, really important biologically, especially the formation of the amide bond that I mentioned last chapter, because that's the bond that keeps our proteins together. And then we're going to talk about bases. The main organic base we're going to be learning about is amines. We sort of learned about ammonia being a weak base when we did acids and bases. But now that we know that ammonia can form a positive charge on the nitrogen, we can now figure out that if you attach an NH2 group or an amine group to a long chain carbon, or a short chain carbon for that matter, that acts as a base as well. So let's jump into dealing with some of these different functional groups. So of the general groups, these are the ones we're going to be dealing with as far as the acids go. The first one being carboxylic acid. So we're sort of familiar with basic carboxylic acid. When carboxylic acids react with alcohols, they form esters. So this would be from the carboxylic group, and this would be from the alcohol group. They also can react with halogens to form what's called an acyl halide. And that would be when one of the halides kicks off the hydroxyl group, or the OH group, from our carboxylic acid, and then replaces it with one of the halogens, bromine, fluorine, iodine, chlorine. And then amides, where we have a carboxylic acid up here, and then it reacts with an amine and forms that amide bond. So here we have our carboxylic acid group, and then down here we have our amine group. Some of the examples would be carboxylic acid. We just basically name it, since it's always going to be at the end. We're always going to have this group at the end of the molecule. We basically just figure out how many carbons there are, what is that R group, and we give it that name. So since we have 1, 2, 3 carbons here, propane becomes that's hard to say, propanoic acid. And then up here we have propanoic acid again. This time it's react with methanol because we have an oxygen and a single carbon attached to it. That would be methanol. So we give it the name methyl propanoate. And then here we have propyl again, man, I'm going to have the hardest time with this. Propanoic acid reacted this time with chlorine. The chlorine kicks out the hydroxyl group and we're left with propyl chloride. And then if we have an amine, we just call it propanamine, which at least that's much easier to say, right? So here's some of the summary on naming these things. Now, aldehydes, we remember we dealt with aldehydes, ketones, and carboxylic acids in the last chapter. So we end it with al to let us know that it's an aldehyde. If it's a ketone, we end it with ONE to let us know it has a carboxyl group in the middle. And with the carboxylic acid, it becomes oic acid. The halide, we end with YL or OYL and then the name of the halide. We haven't dealt with acid anhydrides. That's basically, we have two carboxylic acids come together, and a dog. They come together, kick out the hydroxyl group, and then you're left with basically two carboxylic acids brought together and linked by basically an ester bond. So we call that an anhydride because anhydrous means it's lost water. Ester, we end with O8. Lactones, we're not really going to deal with much. It's just an ester that's in a ring. And then amides, we're going to deal with a lot at the end of this chapter. Aren't we, Jerome? Yes, we are. Okay. He's not excited. So a lot of people have been asking about the priority of groups, and I've been thinking about it myself because we didn't really touch on it. Which groups do you name first? Who gets priority when you're naming? Let's say you have a group that has a whole lot of different substituents. What do I call it at the end? What would be the parental group? And then what would be the substituents? This will give you an idea how to do that. So carboxylic acids are basically the king of organic molecules. So that comes in first as our priority. So if there's a carboxylic acid, then we automatically, no matter what else is on the molecule, we name it a carboxylic acid. And then every other thing would be a substituent. So if there was an alcohol group, a hydroxyl group on it as well, we would still call it a carboxylic acid, but then we would name it, 1-hydroxy or 2-hydroxy or 5-hydroxy or whatever it is, acid. Sulfonic acids, we're not really going to be dealing with much. It's basically the same thing as a carboxylic acid, except instead of having carbon in the middle, it has a sulfur. And next comes esters. So you can see that a lot of these are, of the high priority groups, are either carboxylic acids or they are forms of carboxylic acid. They're reactions, products of carboxylic acids. Then comes esters, acid halides, and amides. So those are first 5. So the next 5, nitrile groups, which you haven't really talked much about those, but we know that this is a cyanide. If it's a group, we call it a cyano. And if it's a suffix, we call it nitrile. Then we have aldehydes, ketones, alcohols, thiols, and amines. So basically we go from acids having the highest priority down to bases having the lowest priority. Excuse me. And then functional groups that are basically always prefixes that we never give. No, this is much more interesting. That we never give a parental group to are just straight up additions of a halide. So bromine, chlorine, fluorine, iodine. An alkoxy group. So this would basically be part of a, if we have a alcohol, sorry, okay, Jerome. If we have an oxygen connecting 2 carbons, like we would in an ether. So the longer chain gets to be the parental group, and then the shorter chain we give the term alkoxy. Here we just have a methyl group attached to the oxygen and with a longer ethyl group on the other side. So we would just call that methoxy because it's shorter. And then finally, nitro at the bottom. So we haven't really dealt with nitros very much, but TNT, as you probably know, is trinitrotoluene. So that may show up on a test at some point. So I put these 11 groups. All right, see you later. So I put these 11 groups, and I'm going to. I've already put them on the list for referencing during tests and stuff like that. So these lists is already present. So you do not memorize them. But if you could remember that basically it is carboxylic acids and their derivatives first, and then with bases at the bottom. Just look at carboxylic acids and some of the derivatives. So we already know that a carboxylic acid has this group at the end. And it's that hydrogen which is donated, making it an acid. So carboxylic acids, since they have these two oxygens on them, are excellent hydrogen bond acceptors and donors. So here's the donor hydrogen, and then this is an acceptor. So it can form really, really complex patterns of hydrogen bonds. And that also explains why carboxylic acids have such high boiling points, because they form these hydrogen bonds really well. So this proton can easily be deprotonated even with a mild base. So we know that with acetic acid, about 2 out of 1,000 or so will be in the deprotonated version, forming acetate. If you have, in the presence of even a mild base, they deprotonate much, much faster. And so that's why you have very active reactions between carboxylic acids and even mild bases. Just look at some of the properties of these carboxylic acids. So the really, really short ones, like formic acid, acetic acid, propionic acid, they are all, and even butyric acid, 1, 2, 3, 4 carbons. These are the common names. These aren't the scientific names. They all boil at very high temperatures, higher than water, with the exception of formic acid. And they're all tremendously soluble. When you see something called miscible, that means that any ratio of that compound and water are soluble. So I can have 5% formic acid, I can have 95% formic acid. They're both super, super soluble. But the longer and longer these carbon chains get, the more and more hydrophobic they get. And that makes sense, right? Since you get these longer and longer and longer and longer carbon chains, they're forming a greater and greater and greater London dispersion force. And at some point, these groups get so long that the London dispersion force overtakes the hydrogen bonding in terms of strength for that intermolecular forces. And so at that point, these molecules are more stable, bound to each other, than they are to water. And so they become less and less soluble. And so you get something like benzene with a carboxylic acid group. Benzoic acid isn't very soluble in water at all, because those rings are really, really stable, stacked on top of each other. They're flat, they're a planar molecule. So you can stack them on top of one each other and get a lot of close contact, which you need for London dispersion forces. And that interaction with the acid group, the carboxylic acid group, isn't nearly enough to break that bond. And so they'd much prefer having the rings together, being stacked on top of one another, than being in water, making hydrogen bonds. So in naming them, we just find the longest carbon root, as usual. And then we know, again, since it's going to be at the end of the molecule, we don't really have to put a number on it because that's always going to be carbon number 1, wherever the carboxylic acid group is. So for the scientific name, we just put oic acid at the end and then give it however number of carbons there are. So formic acid, that's the common name, since it's made with methane with a carboxylic acid group, the actual scientific name is methanoic acid. Acetic acid, which we're all familiar with, is ethanoic acid, and then propanoic, and then butanoic, and then so on and so forth. So very straightforward to name these particular compounds. Halides, now remember, halides have the carboxylic group, but the OH has been kicked out and then replaced with one of the halogens, like chlorine, for instance. So we just put YL at the end of the R group, so acetyl chloride or hexanoyl bromide. So it's either YL if we have a, or OYL, benzoyl, hexanoyl, whatever the group is that has the carboxylic acid on it, followed by whatever it is, bromine, iodine, chlorine, fluorine, etc. So let's look at some of the reactions of the carboxylic acid. This is the more important part, rather than just naming the darn things. What do they actually do? So the most common is, of course, a neutralization reaction. That's what acids and bases do, right? So we have our carboxylic acid in the presence of a base. So our base would be like a conjugate base, perhaps of some other acid, a stronger conjugate base, or even a weaker conjugate base. Because like I said, bases can remove that proton from carboxylic acids much better than just plain water. And so we're left with the conjugate base of our carboxylic acid and a conjugate base which then gets protonated to an acid itself. So the hydrogen, the proton, changes place. It's basically a substitution reaction. It goes from the carboxylic acid to the conjugate base of another acid, and it just swaps. Now, a really important reaction that carboxylic acids undergo is the formation of esters. So that is when we react them with alcohols. So here we have our carboxylic acid with an R group R, whatever it might be. And then here we have an alcohol, and it's R substituent. We just call it R prime. It may be the same, it may be different. So in the presence of a very strong acid, and generally like sulfuric acid is the one typically used for these reactions, because one of the main things that sulfuric acid does is it dehydrates things. There's a really cool reaction you can do with sulfuric acid. And if we were in the lab, I'd do it for you because it's insanely cool. Where you take sugar and you add concentrated sulfuric acid to it. And what the sulfuric acid does is pull all the hydroxyl groups off of the sugar. And we're not going to learn about this in this particular chapter, but when we do carbohydrates, we'll learn that basically all sugars is just a polyalcohol. It has lots and lots of hydroxyl groups on it. And so if you pull all the hydroxyl groups off it, you're left with carbon. And so that's what it does. It just pulls all the sugar off, and it's an extremely energy-rich reaction. It gives off a lot of heat, and so you are left with just this big pile of carbon, and it's a really cool, very dangerous reaction. So that's why sulfuric acid is used for a lot of these reactions. It's a very strong dehydrating chemical. So when it dehydrates and removes this water, it removes the hydroxyl group from the alcohol, and it pulls off the proton from the carboxylic acid, leaving you with an ester bond, a carbonyl and an oxygen. And I sort of mentioned it last chapter. These are really, really strong smelling compounds that are used a lot in they're put in foods, they're put in various cosmetics and in a lot of different things where you want a really, really nice smell, and esters will give you that. Now the reverse of this reaction would just be called hydrolysis. Hydrolysis is a reaction where water is added to something rather than removed. So if we look at the reaction going in reverse, that would just be adding water to an ester under extreme conditions, and then basically re-adding the hydrogen back to the carboxylic acid, adding the hydroxyl group back to the alcohol, and then removing them. So we call that a hydrolysis reaction. Hydro for water and lysis for breaking. So it's actually breaking the molecule apart by adding water to it. So for esters, we use the ending O8. And so we name it with the alcohol group first, and then followed by the carboxylic acid. So the R group that has the carbonyl on it, that is going to be the acid group. The group that just is connected to the oxygen single, that is going to be the alcohol group. So this we call propyl, because it's got 1, 2, 3, propane. That is propyl, and then this is the acid, methanoate. So because it's just a single carbon, methane. Now down here, we have the opposite. Here we've got 1, 2, 3, 4 carbons. 1, 2, 3, 4. 4 carbons attached in the group with the carbonyl. We include the carbon attached to the carbonyl. That's important to remember. So we have 4 carbons total. You want the total number of carbons, including the carbonyl carbon. So that's 4 butane, butanoate. That goes at the end. The acid goes at the end. What is the alcohol? That's attached to the single oxygen. It's a methyl group, so methyl butanoate, and so on. Now this is a reaction we're actually going to do. This is a reaction we're actually going to do in lab this week. This was a reaction that was basically discovered by accident, because people would notice that when there was a lot of potash around, or lye, basically from ashes, so you would have the presence of KOH or NaOH, like strong bases. If there were these long chain, of course I didn't realize they were like long chain um, carboxylic acid groups around it. I didn't know what the hell they were called. But if you have these long-chained molecules with this same grouping in it. So here we've got our alcohol group on this side. We've got our acid group on this side. So we have an ester bond. And that can be easily broken by a base. And so when that base breaks it, we get the formation of a negative charge on the acid group and the release of the alcohol. So here's our alcohol down here. When you have that, we call that a saponification. The reason for that is because if we have a long chain attached to our acid, we call it a fatty acid. You're probably familiar with the term fatty acids because we're concerned with them in our diet and everything else. All a fatty acid is just a long chain with a carboxyl group on the end. So when we have these long hydrophobic acyl chains, or just carbon-carbon chains, they're super hydrophobic when we get them like longer than, say, 10 or 12 carbons. They can be even longer, like 16, 18, 20, 24 carbons. Those would be very fatty acids. So what happens is that they have a long group that's hydrophobic, and the end of it is hydrophilic. This group, the acid group, readily interacts with water. It forms really good hydrogen bonds, may even be charged, so you can get ion dipole interactions, which are really, really strong. On the other hand, you've got this really, really long chain. And this chain is really hydrophobic. And so you can form very strong London dispersion forces again if you keep these long chains together and away from water. So how do they do that? They form what's called a micelle. Now a micelle basically has all the hydrophobic groups together in the middle of a molecule, and then all the hydrophilic portions around the outside. So basically it forms a bubble where you have the very hydrophobic parts all on the inside and the very hydrophilic parts all on the outside. And it's the formation of these bubbles that gives soap its physical property. And so we'll be actually doing this experiment this week, taking something that isn't a soap at all and turning it into a soap by doing this particular reaction. Now the formation of amides let me erase that. There we go. The formation of amides is where we're adding NH2 to the end of something. Now, an amide usually is a reaction with a carboxylic acid, but it doesn't have to be. Sometimes it can be a reaction with one of the acyl halides. So ammonia can replace hydroxyl if it's an acid, and it can also replace Cl or iodine or whatever. And then when it does that, NH2 then gets attached to the rest of the long chain carbon, and one of the hydrogens then goes along with whatever it displaced. So if it was an acid, it would form water. If it was one of the halides, it would form like HCl or HI or something like that. So that would be the formation of an amide. So when you're naming amides are going to be complicated. So I'll talk more about this on Tuesday. But basically what we want to do is find the longest carbon group again. Now usually that is going to be the carbon group attached to the carbonyl. Usually, but not always. So usually the name is going to be based on that long carbon chain attached to the carbonyl. In this instance, we got 1, 2, 3, 4. That's butane, so that would be butanamide. So we put amide at the end to let us know it's an amide. Now, if there's anything else, if there's nothing else attached to the nitrogen, if it's just carbon and then nitrogen with hydrogens on it, NH2, then we'd be done. We just say it's butanamide. But if there's something else attached, if it's not hydrogens attached to the nitrogen, and it's some other methyl group, ethyl group, some other carbon-containing group, then we will put N in front of the name of the molecule and name one of the substituents on the nitrogen. So here we have a methyl group and we have an ethyl group. So we would go N-ethyl, N-methyl butanamide. We would go in alphabetical order. So ethyl comes before methyl. So we put the ethyl first, the methyl second. In this instance, we have two ethyl groups. So we would go N-N because both, basically we're saying there's two groups and they're attached to the same place. Just like we were naming things 3,3 and 4,4 and 2,4 dimethyl, because basically you're saying I got two methyl groups, I got two ethyl groups, however many groups I have, and I'm telling you where they are. Well, in this instance, they're both attached to the nitrogen. So I would call that N-diethyl. And then in the instance where we only have a single substituent, then we just call it N-ethyl. We don't have to mention the nitrogens there. That's assumed. Because if there isn't a carbon here, then it has to be nitrogen. So we don't mention it. Sort of like a skeletal form. We know we got an ethyl group on. If the only other group is hydrogen, we just assume it's hydrogen and we don't name it. Okay? Now let's look at some of these organic bases. Now the main organic base is amines. So this is ammonia. So we know ammonia can be a base because ammonia can take on another hydrogen. And so one of the definitions of a base is it can take on a proton. It can be protonated. And so we can protonate this, and then the nitrogen gets a positive charge and we form ammonium ion. Well, exactly the same thing can happen when we stick an NH2 on the end of a carbon chain. So here I got my carbon chain and my ammonia. Now an amide group. And again, I can put a hydrogen there and give it a positive charge. So this would be called a primary amine because it's only attached to one carbon group. This has two carbon groups. That would be a secondary amine. This one is attached to 1, 2, 3 carbon groups. That's a tertiary amine. It's got 1, 2, 3. And then finally, you can have 4 groups because we know that nitrogen can form 4 bonds. When it does form 4 bonds, then it has a positive charge on it because then it no longer has its lone pair. It only has 4 valence electrons, and it should have 5. So it becomes a positive charge. We call this a quaternary amide. And this has a permanent positive charge because all these are carbons and we can't readily replace them. So it's not like we can just pop a hydrogen on and off. Those are strong bonds. And so it basically has a permanent positive charge. Now when you're naming amines, it's very similar to naming the amides. So we find the longest chain. That's going to give it the parental name. So we have 1, 2, 3, 4 in this first example. We have 4, so butane. So there's a number of different names we can give this. I know this part is confusing. There's sort of like the proper scientific name, and then there's the sort of more common name. So with butane, generally the scientific name would be butanamine. We just replace, or we just add amine to the end, butanamine. You can also call it butylamine because it is a butyl group. You can also call it 1-amino because this is a substituent, 1-aminobutane. But generally, we only use the substituent name if there's other substituents on it that have a higher order, that are basically considered of greater importance, higher priority. Here we've got a tertiary butyl group, 1, 2, 3, 4 carbons. So the same number of carbons, but arranged differently. So we can call it tertiary butylamine. We can also call it, what's the longest stretch of carbons in a row? Would be 2, or no, I'm sorry, 3. So if we went 1, 2, 3, or 1, 2, 3, so that would be propane. So 2-methyl 2-propanamine. 2 being, that's where the methyl group is. If I have, here I have a secondary amine, I have 2 carbon groups attached to it, then I use the N. So it's a methylamine with another methyl group on it. So N-methyl-methylamine, or I can call it dimethylamine, and so on. So then you use the N when there is more than one carbon constituent on the nitrogen. So here we've got 2. I've got a 3-carbon constituent and I've got a single carbon constituent. So the longest one is 3. So again, propane. So I would call it N-methyl propanamine. All right, and again, like I said, we'll talk more about the naming on Tuesday. So these are the sort of the basic formulas, longer and longer and longer chains. And so, like I said, there's the traditional name, there's the IUPAC preferred name, and other names they're given. And so basically we'll be looking at the IUPAC preferred name as the one we basically want to go with. So like 1-propanamine, or you can put the 1 in between. This is the newer way of doing it, putting the 1 at the end. Again, we don't really even need to put the 1 there if it's the only group. So if you want to just put butanamine, that would be fine. Or butylamine, because it's a butyl group. Either one. Generally, the 1-amino, we don't really use those. Sometimes they're used in labs, but generally not. So these would be the preferred names we're looking for. And I think they're the easiest to remember. So methane, ethane, propane, butane, pentane, we remember those. And so just put amine at the end. Now, if we move the location of the amino group, then you would just put it 2-propanamine or 3 or wherever it is. Remember, trying to give it the lowest number possible. So what are some of the reactions? The basic reaction of amines is its reaction with acids. So as I mentioned before, I can take even a weak acid and deprotonate it. And so chemists use this to their advantage because they can take a weak acid that they want to add to something, or they want to combine with something else, but they need to get rid of that hydrogen. So they can do that by adding a weak base, a weak organic base. So here we have triethylamine. So that would be, here's our ethyl group. So we would have 3 of them attached to the nitrogen. That is a weak base. And so when we introduce it to a weak acid, and a weak acid is phenol. Phenol is a really weak acid. Basically, it's an alcohol. Alcohols are incredibly weak acids. They can be deprotonated, but if it's just water, ain't going to happen. But in the presence of a base, it actually will pull that hydrogen off and protonate itself, so the nitrogen becomes positively charged. Then when we have the alcohol with the hydrogen removed, we call that an alkoxide ion. So we can use this and do other reactions with it. So amines are excellent bases for organic reactions. One of the reasons is they don't require water. You don't have to have an aqueous solution here. If the weak acid you're dealing with isn't soluble in water, for instance, then you can't do this reaction in water. You need something else. Well, then we just put it in a solution of triethylamine. Mix them together. So this will dissolve organic compounds. This, we know the phenol isn't terribly soluble in water. So this reaction won't work in water for a variety of reasons, but it will work in a solution of triethylamine. The other thing that's great about these amines and doing these reactions, we can basically design them to be any strength we want. We can have a really strong base. We can have a fairly weak base. Whatever strength we need to deprotonate that alcohol or that very weak base. So that's the basic reaction of amines. And so I will see you tomorrow, and we'll talk more about the naming and more of the reactions back then, as well as doing our workshop. All right, talk to you soon.